Good afternoon, everyone, and welcome to this October edition of the European Membrane Society webinars. My name is Maria Grazia De Angelis. I am the Vice President of the European Membrane Society, and today I'm very happy to introduce you to Professor Maria Chiara Ferrari, who is going to present a webinar about advanced membranes and membrane processes for carbon capture applications. Professor Ferrari is the chair of membrane separations in the School of Engineering at the University of Edinburgh. She graduated from the University of Bologna, and she also got a PhD in chemical and environmental engineering from the same university. She also was a visiting researcher at the University of Texas at Austin under the supervision of Professor Benny Freeman. She later moved to the University of Edinburgh, where she became first a lecturer and a professor, and then a professor in 2020. Her expertise, of course, as the title suggests, is on membranes for carbon capture and energy application. And in particular, she's interested in developing new polymeric and hybrid membrane materials and processes to tackle environmental challenges using both experimental characterization and modeling tools. She is also one of the 10 directors of the SCCS, the Scottish Carbon Capture and Storage Centre, which is the largest group of academic working on the CCUS in UK, and she was involved in several national and European projects about membranes for CCS. So without further ado, I'll leave the stage to Professor Ferrari, and I hope you will enjoy the webinar.
Thank you, Grazia, for the kind introduction, and welcome everybody to this webinar. I'm really honored to have this webinar for the EMS. So today I will talk about some of the work that we've been doing on membranes for carbon capture application, looking both at the materials and process aspects of the problem. First, I'm from the University of Edinburgh, as Grazia as well. Since the last webinar was from the south of the Great Britain, this time we are in Scotland, a beautiful city, and we have strong links with the EMS, and the summer school of the EMS was actually here in 2019. So as I said, in my group, we look both at material and processes. So we start from materials, we characterize them. So we start from polymers and nanoparticles, and we use them as membranes, and we want to characterize their properties in ideal condition first, and then we also want to determine their properties in real conditions. So also look at impurities effects and stability effects. This is because then we want to use all this data to do our process design. So to design and optimize processes where you can use membranes to do carbon capture. And we look at the different application of carbon capture in different processes. And today what I want to show you is an example, a couple of examples of this process. So let's start with the membranes that we are looking at. In my group, we are not synthesizing materials per se, but we collaborate with a lot of groups around the world and around Europe to produce membranes. We are very lucky that here in the School of Chemistry, we have Professor McKeown that does polymers of intrinsic microporosity. And so I'll show you some of the results that we are getting with these kind of polymers. But we are also working on mixed matrix membranes with conventional polymers, introducing different fillers like hypercrosslink polymers, ZIFs, or other things. We also look recently at facilitated transport membranes, where the transport is not only by solution diffusion, like in classical conventional gas separation membranes, but there is also a reactive part of the transport. And we will see how that is translated in some constraints on the process that we want to design for the separation. as I said, we take the materials and we characterize them. We start with characterization in ideal conditions, so pure gas permeability test, and we test them in a range of temperature, again, and pressure, because we need data at different temperature and pressure, because our process will not always work at the temperature and pressure that is usually reported on the Robson plot, that is usually room temperature. So we need a wide range of data to start with. So we start with ideal pure gas permeability, but we also measure mixed gas permeability and mixed gas permeability in presence of water, because again, that is very important to know when we go to the process design. And I'll show you why in the first example that I'll go through. The last type of measurement that we do recently, especially for facilitated transport, is studying the diffusion inside the polymer using also FTIR. This is because we want to know what is happening in situ, especially with reactive behaviors, because we want to know what affects the transport. In that case, again, to transport these data and these parameters into the modeling of the full process. So we collected all this data, we characterize our membrane widely, and then we use all of this in our process simulation. We build our own in-house code to simulate our membrane module, and we integrated it in a couple of simulation tools for process design. So we use both Unisim design, that is by Honeywell, that is widely used in industry, and recently we also been using GPROMs. And with this customization, one of my PhD students in 2012 won the Unisim Design Challenge by Honeywell. So we use these different tools to use our data and then translate it in performance of the full separation processes. So this is the philosophy behind what we do in my group, and what I want to do now is give you a couple of examples of how this translates in practice. I'll go through two examples, one with classical solution diffusion material and one with facilitated transport, for two different applications to show you the peculiarity of each process. So let's start with post-combustion capture in a classical power generation scenario. In this case, we are looking at the coal-fired power plant where we burn coal with air, and we want to capture our CO2 at the end. What we are looking at here is a subcritical coal-fired power plant and a pure retrofit process. So we don't want to modify our power plant at all. We just want to attach our separation process at the end and then the compression for the CO2. This is because operators don't really like modifying their power plant. And even if in literature there are schemes proposed for that would be more beneficial in terms of the separation and the carbon capture, this is a scheme that would be applicable to any power plant. So we retrofit our membrane process and we aim at recovering 90% of the CO2 that is emitted by producing electricity. Since we are relying on membranes that are not infinitely selective, we need to design a two-stage process. So we have a first stage that is used for the recovery, and then the second stage that is used for the purity. So it's a conceptually quite simple process, and it's quite modular, so it gives us some flexibility also in terms of amount of CO2 and the capture rate that we want to do. So this is the scheme that we propose, and we design it, as said, in Unisim design, where we implement our membrane model. This model can deal with multi-component and various flow configuration, can deal with we can use it with or without a sweep, and it includes non-ideal behaviors and pressure drop. We validated the model against some literature data, as you can see in this plot. It works quite well, and from the model we can follow the profile of all the composition of the different gases. This is an example for a 5 component mixture along our module, along the length of our module. Clearly, we simulate one module, we take into consideration the geometry, and then we can adapt the area and the geometry to the size that we want for the design of our process. So let's go into some real streams. So we wanted to design this process using the polymer of intrinsic microporosity, again, that are produced here in Edinburgh. As an example, we chose to use PIM1, that was the first polymer of intrinsic microporosity investigated. And that was used to draw the 2008 upper bound on the Robson plot here on the top left. So we want to use PIM1, and the reason why we want to use PIM1 is even if the selectivity is not as high as other material, is because it is very permeable. And that's very good for this sort of application, because the amount of flue gas that is emitted for a coal-fired power plant is really large. So we want to treat a larger volume of gas, and so we need a large high permeability to decrease the area that we need. So on the Robson plot, PIM1 would lie here on the 2008 upper bound, and these are data usually taken in ideal condition. So for pure gases. But in a flue gas from a coal-fired power plant, we have more components, and these are just the major components that we have. So 13% of CO2 in nitrogen with a bit of oxygen and a bit of water. And this influences clearly the performance of the polymer. And so we need to take that into account when we design the process. This is because, for example, if we think of water hinders the permeation of CO2. There is a competitive effect between the two in the permeation. And so if you look at some of the data that we've taken in the lab, if you take CO2 and you start increasing the amount of humidity that you put in the feed, you have a decrease in the permeability of CO2 compared to the dry stream. And that's quite dramatic and would have a very dramatic effect on your process design. Not only that, so we need to take into account this degradation, but also PIMs are known for having a very high free volume to begin with that tends to collapse over time due to aging, physical aging. And so that needs to be taken into account again. If we want to design the process, it's a bit unrealistic to design it on the data that we get as the first point that we get on day one of casting of the polymer without the aging. There have been proposed strategies in the literature on how to stop this aging, for example, with mix and matrix with PAF that reduces this aging, and that would be beneficial for the design. But for this exercise, we will try to design with both systems. So this is if we account water and if we account for aging, so we need to take into consideration the decrease in permeability. Not only that, flue gas also has some impurities, SOx and NOx, if you're treating flue gas from a coal-fired power plant. And even that has an effect on the permeability. Again, we took some data after exposure to impurities. In this case, the experiment was a little different. Instead of having permeating directly flue gas from a power plant, since we can't get our hands on that, we used a different kind of experiment. So we exposed our membrane to synthetic flue gas that comes dry in a cylinder. You can expose it. You can expose your material to that, adding also a bit of water, and then we remeasure the permeability at regular of pure CO2 at regular intervals. So if you look on the left, this plot, this is the permeability of our material just in contact with air. If we start exposing it to dry flue gas, so just to the SOx and NOx with the CO2, and then we measure the permeability again, we have decrease in the permeability over time. If we add also a bit of water just during the contact, we can see that the decrease is even more dramatic. And that is because something is happening to the polymer. So there is degradation going on. Same also for the permeability of nitrogen. So something is happening during the exposure to these contaminants, and the presence of water with the contaminants is even worse. And that is explained by these spectra, taking the FTIR. As we put our membrane in contact with the flue gas, we see an increase of the peak at 1730. And that's the stretching of the carbonyl groups. So the hypothesis is that we are looking at an acidic hydrolysis of the channel group on the chain of the PIM. So our material is degrading and therefore is losing performance. So this is the part where we characterize our material. Let's see the effect then on the process. We can evaluate and design the process that I showed you, so the two-stage pure retrofit for the different version of the PIM1. So we can design for the pure polymer at the first ideal measurement. And if we do that, we can optimize our area for the two stages that I show you and calculate the energy consumption for what we wanted, that is a recovery of 90% and a purity that is suitable for storage. If we do that, this is what we'll get. But then what we wanted to see is what if then our material is degraded? So what is degraded because of aging, exposure to water, or exposure to the impurities? So if we keep the same design, so the area and the process are exactly the same, we can see that we have a drop in recovery to 55%. So the purity will still stay high because while our polymer is aging or degrading, the selectivity goes slightly up. So we have an increase in purity, but a massive decrease in recovery due to the decrease in permeability. And that becomes a problem for the operation of the process, especially in the case of carbon taxes, where you pay for what you are emitting. For the sake of comparison, we also applied the material after the mixed matrix with PAFs, and the same process would retain some more recovery. So if we are able to stop the degradation or the aging, we are pretty close to the original design. We can also try, so this is evaluating the process if the material changes over time. That clearly is not ideal. We can also decide to design directly the process for the condition at which the process is acceptable, so at the 90% recovery for the three different cases. And if you do that, you can see that for the aged version of the PIM, we have an increase in cost. And this is the levelized cost of electricity. So the cost of the electricity over the lifetime of the plant that would maintain a revenue for the plant. And you can see that there is quite a big increase if you design a process now with a membrane that has a lower permeability than what we plan. This is all calculated with quite low carbon cost, but you can see that what determines the increase is mostly the capital cost related to the degrade performance of our second case. So this was the first example just on pure electricity production and pure retrofit using a solution diffusion membrane, high permeability and relative low selectivity. We are now moving to our second case. Since in the recent year in the UK, the focus of carbon capture has moved to industrial capture, so the capture of CO2 from industrial plants where you don't have the option to move to renewables to avoid the emission. This second case is about cement production. And we are looking now, instead of a solution diffusion membrane, we are now looking at facilitated transport membrane. This work was part of a European project, Horizon 2020 funded, that is called NanoMC2, that had 11 partners, where we wanted to develop materials for facilitated transport. So again, we wanted to overcome the Robson upper bound and move to the area that is of interest for CCS, so high selectivity and high permeability, improving the selectivity of the membrane using the facilitated transport mechanism. We focus on cement because it's one of the sector where there is the largest emission. So the production of cement accounts for more than 70% of the global emission of CO2. And the demand is projected to increase by 12 to 23% by 2050. So production of cement is not slowing down at all. There are some proposals to do low CO2, low emission cements, but the vast majority of the plant will keep producing CO2. The cement plant is also interesting because CO2 is emitted as part of the production of the clinker. In the picture, you can see a schematic of a cement plant where the raw material is firstly is milled and then is sent to a series of preheater that preheat our raw meal before it gets into the calciner and then the rotary kiln, where our reaction for the formation of the clinker is done. So this is the reaction to produce the clinker, where CO2 is part of the reaction. It's one of the products. If you look at the balance of the process, 30–40% of the CO2 comes from burning the fuel that you need to reach the temperature for the reaction in the rotary kiln. But the rest comes from the calcination. There are roadmaps for the transition of the cement industry to low emission, and there is some scope for thermal management and fuel switching, and also reduction of the clinker component in the cement to reduce the emission. But if we want to go to more than 50% emission reduction, we need to apply CCS to this process. So we need to capture the CO2. And in this work, we propose to do it with facilitated transport membrane. So as I said, instead of relying only on the solution diffusion mechanism, in this case, we are also using the mobile and fixed carriers to interact with CO2 and facilitate the transport. So this is a schematic of what is happening. We have our CO2 that reacts with the fixed carriers that are usually polyamines, or with the mobile carrier that are still usually present amine group, and that adds an additional mechanism for the CO2 to move through the membrane, and that is not available for the other gases. And that increases the transport, and so the permeability and also the selectivity. As I said, usually these materials based on polyamines. Polyvinylamine is one of the most common, and then you can add other component to the membrane. For example, this is an example that we investigated during the project, where we add some nanocellulose to the PVAM to increase the stability of the material, and then also some aminosilane to increase the potential for the facilitated transport. This facilitated transport, as suggested here in the schematic, is enhanced by water. Water interacts with the amine group and the CO2, so it's part of the mechanism. And so we want to exploit this mechanism to the full, and so we want to use also water, to have water this time in our feed stream. So instead of water hindering our transport, like in the previous example, now water enhances the transport, and that is crucial for the transport, and so it will become crucial also in how we design our process. Some other example of this is another system that we investigated during the process. This is in collaboration with NTNU, where we have now a polyallyl amine with graphene oxide for stability and polyvinyl alcohol. As I was saying, if you increase the amount of water in your feed, you have an increase in the transport of your CO2, and that translates in an increase in selectivity toward till a certain point, and that will benefit your process. Another feature of facilitated transport membranes that becomes quite important for process design is the behavior as a function of the CO2 partial pressure in the feed. So as we increase the partial pressure in the feed, we see that there is a decrease in the permeance of the material. And that is due to the fact that we have effects of saturation of the carriers. So we can't enhance the transport after a certain level because we finished the number of carriers that we have available for our transport. Again, this is quite important and is quite different compared to the solution diffusion membrane, where the driving force for the separation and so for the transport can be simplified to the difference in partial pressure across the membrane. So usually you want to increase the difference in partial pressure to the maximum, and that translates in either pressurizing the feed or putting the permeate at vacuum. In this case, the benefit is not present. So if you increase too much the partial pressure, you will lose impermeability because of this saturation of the carrier effect. So again, using this membrane, you have to, when you go and design the process, you have to take into consideration completely different constraints. Let's go to the simulation. So we were lucky to have a cement company in the consortium, and so we had the data available for a specific cement plant in Italy. That was the grey clinker line of Colosem in Gubbio, Italy. This is a plant that uses the dry process that I presented to you before, with a production capacity of 3,000 tons per day. The CO2 generation is 0.8 ton per CO2 per ton of clinker, so you can imagine that this plant is producing a lot of CO2 that we could capture. So we base our simulation exactly on this plant. And this is quite important because cement plants are scattered in all over Europe. Will keep to be scattered all over Europe. You don't want to produce cement and then transport it for a very long road. So the production of cement will still be delocalized, and so we need to make sure that we can apply our carbon capture to the specific plant that we have. This is a schematic of the plant where you can see the countercurrent flow of the gas and the solid and all the units that I mentioned before. So the initial mill, the preheater, the calciner, and the rotary kiln where the reaction takes place, and so where we are producing CO2. And then the cooler where we cool our solid, and while the gas comes out on the other side after the dust filter. The flue gas at the end of the process now is as this composition where there is 11% of CO2 in the dry gas. And this comes after dilution of the excess air coming from the cooler that was used to cool our solid that we produced. This is quite important. This value is not far away from what we've seen for the 13% in the coal-fired power plant. And usually membranes are better at higher concentration. So we look at the process in detail since we had all the data available, and we look at this stream. So before dilution with the excess air, the concentration of CO2 is actually way higher, is 28%. And so we consider that a better place where to put our membranes and to use this concentration. And so we propose to modify the plant to still retrofit our carbon capture plant just at the end, at the flue gas after the production, but avoiding the dilution, so breaking the connection with the excess air. This might, depending on where you are and what you have, specifically in the raw mill. So what are the components of the raw mill that are usually localized? Again, as I said, cement is pretty specific. Usually the cement plant is near where you have the raw material that you need to use for the production. And so the raw material tends to change quite a bit. So depending on what you have there, it might be necessary to have additional treatment of the flue gas to protect the membranes. But that, again, is quite specific. As I said, though, we want to use the high concentration at 28%, and we put our facilitated transport membrane there, followed by the usual compression train. And since we are dealing with facilitated transport, we want to keep it humid. As I show you, we need water, and so we use also a steam sweep to increase the performance of our membrane. So we are now looking at facilitated transport membrane, way more selective than what we had before. So now, if you remember, we had the selectivity of 20 before. Now we are working with the selectivity of 300. And that means that instead of having two stages, I can live with just one. And that with the idea that this will help my capital costs of the process, and also will reduce complexity of my process. So this is now the scheme that we are dealing with, where there is only one module, but we have an additional component that is the steam that is used in the sweep to create the driving force. Again, as I said, we don't want to pressurize too much because that will be detrimental to the permeance. So this is the scheme. We are still designing for 90% capture and 95% purity in the transport. And we want to investigate different parameters. So we want to see pressure in the feed, the temperature of the steam, so the steam grade, and the flow rate, and what would be the optimized design. So we investigated all of this and built a lot of this plot for different cases, and then we compared it also to state-of-the-art solution diffusion membrane, again keeping the 2 stages as in the coal-fired power plant example that I showed you before. In this case, we are basing our solution diffusion membrane to what is published in the literature state-of-the-art, so on the Polaris membrane proposed by MTR. So let's come to the result. So if we look at the sweep temperature first, so at the grade of our steam, we can calculate for that process that we propose the steam requirement and the power consumption for our compressor mainly, and the area of the membrane that we need. And we can see that as we increase the temperature of our steam, we have a decrease in the area of required for our process related to the performance, and we have a decrease at 75 degrees of the steam requirement, but with a slight increase at 90 degrees. Same for the power consumption. If we compare it to the solution diffusion membrane process, there's no steam requirement there, so in a sense easier on that side, but the area required is way higher, and also the power consumption for the compression is higher. To compare different processes, it's also useful to look at the specific primary energy consumption. So to compare processes that use steam or electrical energy, SPECA, the specific primary energy consumption for CO2 avoided is quite useful, and is defined as the difference in the equivalent primary energy consumption scaled by the equivalent specific emission of the plant with and without carbon capture. So we are taking into account the energy consumption scaled by the direct and indirect emissions. So since we are taking into account also the indirect emissions, what we are using as a source for steam and for power is affecting the value of our spec. And here is where the specific site where our cement plant comes into play. We were in Italy for this, so we use the energy mix, for example, for power, the energy mix of Italy and the emission related to that specific energy mixture that is different according to countries. So since we use that for the power, for the steam, we can devise 3 different scenarios where our steam is coming. There's no steam in a normal dry process cement plant, so we need to find some steam for our process. We devised 3 different scenarios. One is called import, one internal, and one natural gas. For the import scenario, we import our steam, we buy it from a nearby CHP plant. In the case of the internal scenario, our steam is completely generated by waste heat inside the plant. For the natural gas boiler scenario, we are building a new natural gas boiler in our plant to generate the steam that is required. If we look at the 3 different scenarios now and the specca for the 3 different scenarios at the 3 different temperatures, again, at 75 degrees, that's our best scenario. And the best, as expected, the best option is to have all the steam raised internally by waste heat. The natural gas boiler scenario in this picture as the highest specca compared to all the others. We can compare also to other technologies, and that's why we chose to use the specca. And we can see that for our facilitated transport membranes are slightly higher than the solution diffusion membrane that I just showed you. We can also compare to other reference cases, MEA, that is the classical amine process based on monoethyl amine. And we can see that in comparison, our specca is slightly lower at 75 degrees, while the best option is for membrane-assisted liquefaction. That is a membrane process using solution diffusion membrane, but run at with a liquefaction process after. That seems to have the lowest specific energy consumption. This is for the technical part, but we need also to evaluate the economical part of the process. So in this case, for the economic analysis, we based our consideration on 2 parameters: the cost of clinker, that is estimated including all the capex, the fuel cost, the raw material, and the electricity and the operating and maintenance cost, and the cost of CO2 avoided. That is calculated based on the cost of clinker with and without carbon capture, scaled by the equivalent specific emission with and without carbon capture. Again, in the specific emission, we are including also the indirect emissions, so the emissions that are coming from the power that we are using, or the generation of the steam in case we are importing the steam. Okay, so these are the economic performance of the base plant. Some of the assumptions that we use, these are quite important, as we will see, especially the natural gas value for the OPEX, but these were done on 2016 values. So will change if you do it for 2022. But just for reference, in this case, the cost of clinker was 61, more or less, euro per ton of clinker. And this is the breakdown of the cost, where variable, fixed, and OPEX and CAPEX all take more or less 30% of the cost. If we look now at our different temperature for the steam, we've seen the technical data before, so the area decreasing with the higher temperature in the steam, and while the steam and power requirement were optimal at 75. If we look at the cost of clinker and the cost of CO2 avoided, we now see again that the 75 scenario is slightly better than the 90 and better of the 60 degrees. And the value that we are looking at for clinker now, for the cost of clinker, that if you remember was 61 euro per ton, is almost 120. So we are almost doubling the cost of our clinker. And if we look at the breakdown for 75 degrees, the increase is due to the variable OPEX that are taking a higher proportion of the pie. If we look now at the different steam scenario that I just proposed to you, again, we can look at the cost of the clinker and cost of the CO2 avoided. And you can see that in this case, the internal and the import scenario are better off building a natural gas for the cost of clinker. And that is due to the capital cost that we are adding if we want to build a completely new natural gas boiler on our plant. But interestingly, the internal and the import scenario are quite similar. That is quite dependent on the cost of gas that you use for the import scenario. So clearly this would change today, where the cost of gas has changed significantly compared to 2016. We can also compare our best case, that is the 75 degrees, to the other technologies in terms of cost. And you can see that actually the facilitated transport membrane have a cost of clinker that is comparable to the other technology, slightly higher than the reference amine plant, but lower than the MAL, the membrane-assisted liquefaction. If you remember, the membrane-assisted liquefaction had a very low specific energy consumption, but the capital cost involved in building the cryogenic part of the plant raises the cost to 120. And for this cost of CO2 avoided, again, we are in line with other technologies. We've done what I've shown you so far was for that modification of the plant with this 90% capture at 28% of CO2 in the stream. But we've done a bit of sensitivity analysis as well. So we look at the effect of the capture rate on the variable OPEX that, as you remember, was the largest part of the cost of clinker and the largest contributor. And as you can see, if you decrease the capture rate, then you decrease clearly the variable OPEX contribution. And so there is this interest in having a lower capture rate using membranes in plants. So if the advantage of our membranes in that scenario would be higher. Finally, the last thing, we've looked at the effect of the concentration on the performance and on the variable OPEX. This time just at 75 degrees, that was our optimal case. If you remember, 28% was the concentration in the flue gas before the dilution, but after dilution, the conditions were at 11. So we looked at the range of concentration to see the flexibility of our design. And as you can see, if you decrease the concentration, you decrease the variable OPEX. But the problem is that you can't reach anymore the 90% recovery that you want. So again, going to lower recovery with the idea that starting a lower recovery at least does something might be beneficial for this application. So in conclusion, I hope I show you that novel membranes can be used for retrofit carbon capture option. There show promises in comparison with others. That there are some advantages depending on the process that you are considering. So depending if you are looking at power or industrial scenarios, and some of these might be site specific. As I said, in cement plant, you don't have steam, so you have to provide it. Might be that in other processes that could be an easier application. Reduced capture rate would be beneficial for membranes, so this comes to is proposed as a solution to start carbon capture now instead of waiting for having a very economical solution directly at 90%. And I think that also my point is that when you are developing a new material, you want also to start thinking at the application in the full process and how the new material performance will affect the design of the process and how you can take that into account in your design. Finally, I didn't show it, but we just look at the economical assessment, but clearly also other environmental costs should be taken into account. And so a full life cycle analysis should be done for this process. Thank you for your attention. Finally, want to thank the group that has done the work, my group in engineering, and also the School of Chemistry, Professor Mercune's group that provides us the material most of the time, and the funders, the PSRC, and the Horizon 2020 project. Thank you.
Thank you, Chiara, for this very broad presentation. And while introducing you, I forgot to mention that you were also member of the European Member Society Council. Sorry about that. You used to be. So I think this is a very broad topic, and I have so many questions to ask while we wait for the questions from the audience. And I think you kind of answered many of the questions that arise during the presentation, but still I have some more. And one of my questions was starting from the solution diffusion membranes, the PIM-based membranes. I noticed that you compared PIM with PIM aged and with PIM containing an anti-aging filler. And when you compare these different membranes, you notice that you have a lower capture rate, right?
So the first evaluation was done at the same process. So the idea was to show that if you design the process at a certain value and then your membrane changes over time, your capture rate is going down.
Yes, exactly. It is stable. The energy consumption goes down too. So here the energy consumption is for compression of the gas.
Yeah, it comes from the fact that in your compression train you have way low
the compression of CO2. Okay.
So this is the energy consumption of the whole plant, and so in your compression train you will have less.
You have less CO2.
Process.
Okay, so I understand. I thought this was the compression before the membrane separation.
No, it's the energy consumption of the full separation and compression. Sorry.
Makes a lot of sense. And I was curious because I have heard speaking about the cement plant. You compare to several technologies. What about the calcium looping?
Yes, there. So if you in the reference that I use for comparison, there is also a calcium looping option that as depending on. If you go into calcium looping, the best option is to integrate completely the calcium looping inside the process. At that point, it's not a retrofit anymore, so that's why I didn't put it in there. If you use the calcium looping as a retrofit, you don't have many advantages because actually it becomes comparable to the other. The advantage for calcium looping that is there for cement is the best option if you completely integrate it. But at that point, you need to completely change the calciner. So it's probably a solution that is available for new built cement plants more than existing cement plants.
It's not comparable. Okay. And I was kind of surprised to see that the membrane-assisted liquefaction process, which, by the way, I know nothing about, is so competitive.
It is competitive in terms of SPECA, energy consumption. The problem is the capital cost for the building of the the cryogenic unit, then brings the cost of the cement so high. If you can improve the performance of the membrane, probably also that will change, but still the problem lies in the capital cost of the process there.
And what membranes and what temperatures will you be using in such a process?
No, in this reference, the membrane is
not specified.
It is specified, but is operating at room temperature. So
okay. So the membrane and then the liquefaction. Okay.
Exactly.
Interesting. So I'm still waiting for questions from the audience. There are some people connected, but still too shy to ask a question. So another question I have, I'm sure you have done in the past combination of membranes with other capture technologies, although you didn't show them in this presentation.
So there's a lot of literature in combining membranes with amines, for example, and some with membranes with adsorption processes, with the idea to having a first pre-concentration with membranes and then the final purification using the additional technology. There's a bit of debate on how useful that would be and how the cost would be. So if you go into the literature, there's opposite views on what that would achieve. Again, what has emerged that the best integration would be membranes with assisted liquefaction. That seemed the best option for integration, with in recent year looking at actually operating the membrane at lower temperature. That seems to be the best option. There are not many data though operating the membranes at low temperature.
Okay, thank you. I have a question from the audience. Okay, you can maybe read it on the screen.
So for the post-combustion case, what we consider, I don't remember specifically the level, I admit, but it's a combination of feed compression, so sludge compression on the feed and vacuum. And the level of vacuum that we chose is around 0.25 bar, with the idea that you can't go lower in industrial processes.
You cannot.
It would be unrealistic. It would be too costly to go lower than. So yeah, that's the. If I remember correctly, those are the value. But there is a paper on that, and if I can find it. In this paper, you can find all the details of the post-combustion case.
Let's see if there are other questions from the audience. I'll leave another minute. Okay. Let's see, normally when we try to close, someone shows up. So let's pretend we are okay. So there is another one indeed. Yeah, I think you will see it in a second on the screen. This is an interesting one. Which membrane cost you consider?
So again, for the cost is clearly one of the variables that that might change a lot your cost. We chose to stick to what is used in the literature of 50 euro per square meter, in the idea that when we get to the these areas of membrane. So we've managed to scale up our material, and so we have already taken advantage of economy of scale. So that's the also usually for the module is not only the membrane cost, but is more of the what is around, so the casing, and so that was our choice.
Okay, thanks. So I think now time is up, and we have to end this very interesting presentation. And
thank you again for the invitation to the EMS. It was really honored.
Thank you, Chiara. It was very interesting. I have a few announcements to make. First, that we have the upcoming Euromembrane conference. That is the flagship conference of the European Membrane Society, which will take place in Sorrento mid-November. So we hope to see everyone there in person, finally. And I would like also to thank Dr. Elena Tocci, who is behind the scenes. She is the technical supervisor for this webinar, and Marco Stoller, who's also the technical coordinator of the EMS webinars. And again, on behalf of the EMS Council, I thank you again, Professor Ferrari, and everyone in the audience for contributing to the success of this webinar. Thank you.
Thank you.